Thank you. Actually, I feel so Andy's talk is so inspiring. He mentioned several keywords. Big data is inevitable, and also several key elements for big data. So the first one is data itself, and the second one is the analytical models, and the third one is tools. Then last one is skills. Of course, I'm not the person to talk about the data, and also not the person to talk about skills. And also, I'm not good at modeling. But then today, maybe I wish to share with you one of the potential tools in big data. So that is called extreme learning machines. This actually was proposed 10 years ago. So finally, due to the contribution from the whole world, it becomes, I say, more and more mature, but the good things yet to start. So we, after today's the so-called sharing session, so I wish some more contribution maybe from the audience in the future as well. Anyway, it's a new things. Today, I will mention the several points of the extreme learning machines. First, what is an extreme learning machine? Second, what is the potential relationship with the big data, as well as Internet of Things, and also possibly what are my observation on the so-called machine intelligence and human intelligence. Okay, so let's start my talk from one dream. So many of you actually know neural network. Neural network now has become very popular, very hot. So actually 15, 16 years ago, so Rosenblatt, who was a biologist, come a dream. He proposed a multi-layer feed-forward neural network, which is called perception. He said that perception can help computer walk, talk, see, write, and even reproduce itself. But nowadays, people will believe this dream actually very realistic. However, 60 years ago, when he came up with such a dream, many people didn't believe this dream is true. So this is why many of you also know there is fighting among different group of peoples. So one of the typical fighting, very famous one is between Rosenblatt and Minsky. So Minsky, who was awarded Turing Award in 1970s, he wrote a book in 1969, and in that book, he proved in theory, because Minsky is the mathematician, he proved in theory, say, actually multi-layer perception actually couldn't resolve XOR problem. XOR problem actually is very, very simple. What is the perception model Minsky used? It just have a two-layer, input layer and output layer. He proved such a two-layer network couldn't resolve XOR problem. Of course, the Minsky is so influential. Then the whole world suddenly feels surprised. So such a feed-forward neural network can't resolve XOR problem. How about more complicated applications? Of course, useless, impossible. So then this almost killed the research in neural network and also influenced artificial intelligence. So that is the finally resulted in AI winter in 1970s. Okay, so now we come back to see this so-called fighting. Of course, the perception or Rosenblatt actually is true, because now is a deep learning can solve these many, many things, even can beat human in games, playing games, right? So you see, 50 years ago, such a small things couldn't be realized or recognized by human. So now you see everything is so apparent. So this tells us a small step in research in AI could be very difficult in past years. Now we say, oh, so simple. And when you go back several decades ago, it would be very, very difficult. So now we say perception can do many things. We true. we believe it's true. Now we know, many of us also know, now we are coming to the machine learning era. I classify machine learning actually had the 3 waves. From the 1950s to 1980s, I call it a warm-up stage. So why this warm-up stage? When actually the first generation of computer produced, people already dream AI, right? Machine learning, etc. But definitely in those days, it's very difficult to come out the true AI, artificial intelligence, or can imagine computer can finally beat human, because computers are not powerful enough. No efficient algorithms then. And the most critical issue is we do not have enough data. No data means no food, no knowledge. So how can you come out of intelligence? From the 1980s to several years ago, I classified the 2010. From that 30 years, around 30 years, we call research-driven. So why it is called research-driven? Actually, those days, computers already powerful enough, actually much more powerful than human neurons. And also many efficient algorithms already developed. Actually, many of you say deep learning now is very popular. But remember, most of the fundamental algorithms which are used in deep learning now developed in 1980s, or even people say 1960s, 1970s. Either BP developed in 1970s or 1980s, whereas memory machine, or most of them in 1980s. But the problem is we do not have data or enough data those days. So you see, even 15 years ago, when the researcher tried to publish a paper, right, find some benchmark data, very difficult to find benchmark data. So this is why some researcher put data online, say we call benchmark data, right? Those days, even you want to write a paper with several thousand samples, actually it's not so easy to find several thousand data. If we have several thousand data, those days we already call big data, right? So now you say several thousand, so what? We have millions or tens of millions or billions of data already available. So those days, I found it's very difficult to have the to have their AI or machine learning to be recognized in industry. So many researchers have good ideas and sit in office, enjoy their ideas, right? So I say research-driven, because most of the things driven by the scientists or professors. But since the 2010, I think the world is changing, especially after the iPhone produced. You see, iPhone, they have their iPhone 4, it's small things. But that thing, I think, is a significant change in the whole world. Because this, since several years ago, we know the computer is powerful enough. But more important is smart sensors everywhere. For example, we have this iPhone 4. Then we can access internet. And then we can take picture everywhere, right? We can upload the data everywhere. We can share data with everyone. But 20 years ago, very difficult to find the data. You want to take a photo? Not so easy, right? Have to bring a big camera to go somewhere to have, to take some of the picture. Very few pictures available. So now is everyone can share the data, etc. So even in our iPhone, you see how many photos in our phone? Several thousand. 20 years ago, we have how many photos we have? Very few, several. But now several thousand. We take a photo everywhere. We enjoy taking photos. But how many of us are really looking at your photos you have taken? Very few, right? So that means we have too many photos to look. We are not surprised of data anymore, right? Or on data. But look at the company. Can the company forget the data? Impossible. As Annie just made, that is the asset. You can't, as a company, can't give away data. Because you give away data, you give up opportunities. You do not know the patterns behind. You don't know, so what is the opportunity behind? So data, I say data is money. So previously we say data mining, I say wrong. Now we should say data mining money from data. Okay, so the whole world is now changing. We can't run away from the data. So no matter you believe or not, the whole world is inevitable. We are going to machine learning 0, okay? So that is the truth. But when we talk about big data, I say big data is inevitable. That means from now, even say several thousand years ago, million years ago, several thousand later or million years later, we are always in the big data era, right? So it's then the key points for machine learning. What is the necessary conditions? The three necessary conditions for machine learning. The first one is the powerful computing environment, okay? So actually it's become more and more powerful. Then the second one is, of course, big data. But from academic point of view, I would prefer to call it rich and dynamic data. Because big data, I say, even from now several million years later, also in big data. But it does not tell us so-called key points for research. From research point of view, I say rich dynamic data. The rich means that data should be rich enough to represent your information, your applications. From academic point of view, from research point of view, I say too big. The data is too big. I don't think it will be good because it may have too many noises, or it may have the cause some overfitting. It's similar to kids. A kid, if you have some particular exercise or topic, say math equation, just one book or two books enough exercises for exercises. If you give the kids 100 similar data, similar books, the kids will be overtaught. And then finally, he will become clumsy. So the same things for big data. So the data should be good, rich enough, but too rich, too big, it will be a problem, okay? So the second thing is a dynamic. I say dynamic data should be changing. You can't use the data you collected 10 years ago to do something for today, say stock market. You collect data 10 years ago, okay, good, for that period of time, but now, how about now? So you should be changing. Okay, so this is actually, we can't do, these are all our key points, right? Data are always going up. Sometimes we say, okay, even we don't have the good tools, how about we have more powerful computing environment? I say it's a problem. The more powerful computing environment you have, the more compact hardware you have, the more data will be generated. We are always in, face such a difficult situation. So in this case, for machine learning, I think the key points for the future will be efficient learning algorithms. So this is why we focus more on efficient learning algorithms. So this is one of the key topic today, topic for my talk. So when we talk about efficient learning algorithm, most of you know now is the neural network are so popular, all right? Of course, neural network I just mentioned is up and down, on several waves. I did some kind of research. I found actually for neural network, the peak down, always 10 years. You see why 10 years? Perception come out, and 10 years later, go to AI winter, neural network winter. And then BP going up, and 10 years go to a peak, and then SVM come out. The SVM 10 years later go to a peak point, and the deep learning come out. And then SVM also now is dying, right? So it's always 10 years the period of time cycle. So for neural network, most of us use multi-layer network, but fundamental is a single hidden layer feed forward. So that have input, hidden layer, and output. So I want to go to details of the neural network. But the neural network, I say AI winter is 1970s. Then going to the 1980s, neural network suddenly become, I say reviving again. So then the typical point is a Hopfield neural network, the backpropagation come out. And those help revive neural networks. So neural network come out, algorithm come out in early 1980s. Even most of the fundamental algorithm for deep learning come out in early 1980s. But from research point of theoretical point of view, most of theoretical results come out late 1980s or until the middle of 1990s. So two algorithms, two so-called neural theoretical work. The first one talk about universal approximation of neural network. So that means give any target function, as long as number of hidden neurons large enough. So the output of the network actually can approximate target function as close as possible. Then the second, we proposed proof in 15 years ago. Say, give a classification application. As long as the so-called, ideally, the class can be classified, right? Disjointed. Actually, neural net can help us to classify the different regions. So that means neural net can help us do approximation application and also can complete the classification application is good. Because most of the applications either can be considered as the universal approximation or classification application. So good. But the problem, these two algorithms only, these two series only tell us existence of some algorithms. So this, since only there exists such an algorithm which can be used for to do approximation application or classification application. So what are those algorithms? So this is why in the past year, past 30 years or 40 years, people spending a lot of time looking for algorithms. I say the whole world working on looking for algorithms. Okay, almost every university, almost every department in the university, as long as you see power department, you know, electronic department, computer science, even math, even power, etc. So many algorithms have been produced. And when most of those algorithms, when proposed, are considered as biological inspired. But actually, I found something, when I studied those algorithms, I found more study you spend, and then I feel more confusing on the convergence between the biological learning and those conventional learning algorithms. Actually, I found they are diverging. You see, for example, conventional neural networks, most of them are very sensitive to the network size. How about human? Human actually have 100 billion of neurons, and then module by module. Each module can, you know, have the neuron from the tens to 10,000 neurons. We are actually very stable, right? We are not so sensitive to the number of neurons in each module. And also in the traditional learning methods are very different in parallel implementation or hardware implementation. But actually human always run in parallel human brain. And also we can consider a kind of hardware, means protein-based, right? And the traditional learning methods are very sensitive to user-specified parameter, but we can't imagine we have a tiny person sitting in our brain tuning parameter for us every day, or for every behavior, every action. So I'm talking, then someone tune the parameter for me. Okay, because you're talking here, you're talking. Then I'm drinking and something else also he'll help me tune the parameter for me to drink. I think impossible. And another one is, we know different applications require different algorithms. Usually we work in that way. We say, okay, you have a feature extraction, we use PCA. We have the classifier with the SVM, etc. But human, you see, I say many modules are shared by different applications. No matter it's the compression, feature learning, clustering, regression, and classification, etc. Okay, so I want to go to details in each part. But most of them, traditional methods are very time-consuming. But human actually is very, very fast. Okay? So then the other one is traditional methods usually are greedy in accuracy. So when we publish a paper, usually say someone else already published a paper with 98% accuracy. So in order for me to publish a paper, right, at least let's say 98.1%. If we can get the same accuracy as others, 98% or 97.9%, I think most of us, they are not submit a paper because it's slightly lower than others. But brain won't be so great in accuracy, right? So for example, I do classification. Say this is a laptop and this is a cup of water. So what is the separate boundary? It's very easy for me to find. Every time we are actually separate boundary may not be the same. But if you use a traditional learning method, it's a very simple case become very complicated to sampling, you know, and then go lab to find the right boundary, etc. Right? Okay. The finally is most of the algorithm give an application first, and then we're looking for the algorithm. But how about the brain? Brain always sit on top of our shoulder. No matter what application you are given. So that means we always have a brain first and then application. But the traditional learning method always have the so-called application first and then given the so-called algorithm. So I think all those is contradictory to the tradition, to the brain. I mean, traditional learning algorithm and the brain, actually, the learning mechanism are diverging. So the key problem is we know the BB have the local minimum issue, but the brain, I think the learning, the research on neural network in the past decades actually have been stuck in a local minimum in some sense. Because you see, previously I just mentioned, there is a fighting between the perception and the Minsky's, you know. So that means that fighting actually finally tell the truth. Hidden layer important. So Minsky rejected the perception dream because Minsky say, since say multi-layer can do so many things, I can give an example, counter example, perception, multi-layer network with input layer and output layer without hidden layer. So that such a network can't do a simple XOR problem. So finally people found hidden layer is so important. Minsky's example is like tell us, so give a round shell. So have input means eyes and noses, mouths, etc., sensor, ears. And also output layer means cortex, etc. But the shell itself, nothing inside, means empty shell, means no central system, no hidden layer. So that tells us the hidden layer is so important. So in the past decades, almost all the research algorithms studied all the efforts spent on how to tune in the hidden layers, including the deep learning, etc. So I found they may have something wrong. Actually, in the real applications, look at the brain. We usually very difficult to say doing something like drinking water or I see something new. I have to tune in all the hidden layers. You know, the brain is so complicated. So then I found, actually, can we have some alternative research approach? So that is what we call extreme learning machines. We say brain is constructed layer by layer. But for each layer, we can say have a simple architecture. We assume we have an input layer and a hidden layer, then output layer. And then the hidden layer for the brain, actually we have 100 different type of neurons. Okay, so then we can consider the hidden layer as a mapping. So we have the air hidden neurons, then we have the air so-called of picture mapping of the air elements. And then each hidden layer, we don't know the exact formula, activating formula, but we also can use the sigmoidal RBF and some other, Fourier series, etc. So our theory is showing that as long as the hidden layer, the active function is nonlinear piecewise continuous function, and then the hidden layer need to be tuned. If this network is used for feature learning, clustering, regression, and classification. Then in theory, several years ago, we proved in theory, say, as long as the network has the universal approximation capability, as long as so-called the hidden layer is nonlinear piecewise continuous, then we say no need to find any particular learning algorithm to tune in the hidden layers. The hidden layer actually can be random generated, no matter what type of nonlinear piecewise continuous function, even the brain, right? You don't know exactly the so-called output modeling, but we know most of them are nonlinear piecewise continuous function. And then such a network can approximate your any targeted continuous function with the arrow approaching 0 with the probability 1. So the only part you need to adjust or learn is the weight between the hidden layer and the output layer. Okay, so in other words, so we have an input layer, or input data, and then we have an ERM so-called feature mapping. So this feature mapping is known to us. So it's different from SVM, which is unknown, right? So we have random generated. And then here, And also each hidden node, you may not be just the one single node. It could be a sublet as well, right? So then such a network, it would be very simple. So that means we know hidden layer is very important, so it need to be given, but it need not be tuned. Second, the hidden layer, we say maybe the exact formula may not be known to us, but it satisfies universal approximate capability. And meanwhile, we want to minimize training error as well as the width, the norm of the width between the hidden layer and the output layer. So this actually builds the connection between the regional regression theory and neural network generalization theory, as well as the metric series, Fourier series, etc. So finally, the basic ERM model is very simple. So it would be, say, because it's just the random general hidden layer and tuning the output layer. So actually, in many, many cases, the formula is very simple. You can get a closed form solution. So the simple math is enough. So this is very interesting. In real applications, we wish their formula or solution as simple as possible. But when we write a paper, we wish to have some advanced formula given there to show our high standing. So from the research point of view, application point of view, you need to have a trade-off between these two. And then the ERM extremely fast. The other, different from the traditional learning algorithm, which learning theory, which only tell about the existence of something. So here, we talk about this new theory not only give the existence, solve the existing issue, but also give the solutions. So it tells us hidden nodes are very important, but they needn't be related to the training samples, applications. Actually, those hidden nodes, parameters, are not only independent of training data, but also independent of each other. So this is different from traditional learning method. So now I spent several minutes giving some so-called show some experience performance. So for example, for this 3D graphic segmentation, so traditional graphic segmentation methods have to spend 8 hours, okay, on such a case. For ERM, the training time only is 15 seconds, and also get a higher learning accuracy. So this is the real case. So 8 wind farms in Spain apply ERM for wind energy prediction. So that means time series applications, but then predict the maximum wind energy several hours or several hours ahead. So these two graphs tell us the best prediction accuracy and the worst prediction accuracy because of random used. You can see actually it's very close to a real case. And this show one case between the compilation using the compilation of the deep learning and the ERM. So that means use deep learning as the feature learning and use the ERM as a classifier. So this comes from the result done by the Microsoft research in Seattle and Ohio State University. So this is the speech emotion recognition. So the first bar, the blue bar, is done by the hidden Markov model, and then deep learning solution. And this the deep learning plus the SVM. So these two actually come from the deep learning plus the ERM. You can see the overall result obtained by the combination of deep learning and ERM is much higher than the rest method. So this is another application for traffic sign recognition. So this actually is the deep learning server get the best solution result in the several 2 years ago in the computation. And then some team using the combination of the deep learning and the ERM. So they're using deep learning as a feature learning and the ERM as a classifier. You can see the ERM combination of the deep learning and ERM actually achieve the same accuracy as the pure as a deep learning solution. But the shorten the training time from 37 hours, which is based on GPU, to the 5 hours, which is just based on PC. Actually, a lot of group of researchers just purely using the hierarchical ERM, means several ERM stacked together, actually can shorten the training time from 37 hours, which is GPU based, to 1 minute which is purely PC-based, actually accuracy even higher. This result not published yet, okay? So we say the ERM is the, in general, is a single hidden layer. So this is the output of the hidden layer, but the output can be considered a feature. So we can use the ERM as the feature learning, maybe another ERM as a classifier, another ERM as the, another ERM as a clustering, then finally another ERM as a classifier, so several stacked together. For example, using this for action recognition, hand gesture recognition. Traditional method could be PCA plus SVM, so which is we call heterogeneous solution. Actually, we can have the homogeneous solution, means using ERM itself as a feature learning. Another ERM as a classifier means the same material, same architecture, right? Very close to the human brain. And then you can see significant increase training learning accuracy from the 85, 93% to 99%. So this published actual transaction on neural network learning system this year. So when we talk about another application, so material ERM put together, we can using ERM to do the OCR recognition. So using 60,000 data for training and 10,000 data as a testing, so exactly as deep learning. So we have the several ERM stacked together. And then surprisingly, the training time compared with the deep learning can shorten the training time from 20 hours to 4.5 minutes. And then accuracy compared to deep learning also significantly increased. Now we actually can go to the almost 99.7%. I told my student, no need to publish such a result because the same data set. As long as we know the result, then that's fine. So this is actually done by someone else. Actually, is a 3D object recognition. So some team using the deep learning in these applications. So then the deep learning it take 2 days for deep learning to complete the training. The accuracy is at 6.5. So then purely ERM based, so several ERM stacked together. And the training time shortened to 10 minutes. And the accuracy is almost the same. So this actually result just published. Actually, we're going online, I think the early August. So ERM actually we say can be stacked together. So overall, we have the single layer we call generalized single layer. But look at the brain, we have layer by layer. But each layer could be very complicated, right? So this is why we say somehow you can't say exactly one hidden layer. Okay, so some part could be accumulated with the several nodes. So in general, the hidden layer can be random generated according to any continuous distribution function. So it could be uniform distributed, means fully connected. Or it could be some kind of the distribution, which are dense in some areas, but sparse in some other areas. So in this case, we have the come out using ERM theory to explain the local receptive field. We know that convolutional neural network is the local receptive field based, but we can't imagine the brain itself using the so-called convolutional neural network with a rectangle, the convolution operation. We may have some other local receptive so-called field operation in the brain. What is that local receptive operation? Which is unknown to us. But using the ERM theory, you can explain. Because some area is dense, right? According to the ERM theory. Some area could be dense, could be multimodal, multi-peak area. So in this case, you see this local dense receptive field could be considered as the combination of severals. So these severals, those combinations could be nonlinear based instead of only linear based. Look at the brain, many areas are actually nonlinear based. But with this, that means one hidden node can be a sublayer one. So in this case, we can consider convolutional rate is just a specific case of ERM theory. And we also have the pooling as well. So use this solution. So again, we have the multi-layer feed forward so-called ERM, but we don't tune in the hidden layer. So all of them just like a piece building a block by block. Then that's all, without further tuning. And then the training time, based on this log data object recognition data set, using ERM, we can shorten the training time from 13 hours to 0.1 hour, means 6 minutes. But significantly increase the training time from the convolution neural net 94.5 or 96% to 97.3%. So recently, some other researchers come out a result based on the lob, actually can go to almost 98%. Okay? So I say ERM is a step by step. Each layer can be considered one map. So this can be combined with other learning methods. So you say have several, you have the ERM here, in between you have maybe have other classifier or other learning algorithm, or you have the other learning algorithm. This ERM can put in like a filter. So this is different from the traditional so-called deep learning. We know deep learning is layer by layer, but each layer actually will be tuning, right, through iterative way. So after different layers put together, they have a tuning again using BP. But ERM is stack layer by layer. So after stack, no need tuning further. And each layer, no need tuning. So we say in the overall, from like a brain. So we have a layer by layer, have different pathways, then layer by layer. But each layer, overall, we look at the brain is very structured. We have different pathways from the eye, nose, etc. to the cortex. It's very structured. This inherited from the parents, ancestors. So overall it's structured, but locally it may not be structured. So locally it could be random generated, okay? So each layer. And then some area could be a sublevel as well. So in general, ERM focuses on 3 key points. The first, we try to have at least the user intervention. The second, high accuracy. Then third is the real-time learning. So when we talk about high accuracy, it doesn't mean we are very greedy in accuracy, all right? But in theory, we already proved, and also paper published several years ago. So in general, actually SVM compared to ERM, SVM just provide suboptimal solutions, okay? So that is already proved and also proven in theory and also published and have many experiments results issued. Then the next one is real-time learning. So this is why we just choose several experiment results. When the people talk about days, the training time in terms of days, actually we wish to have the training time in minutes or even seconds. So now we actually have the hardware, not only from our team, even from other teams. People can go to the micro level second, even nanosecond, okay? So in general, ERM server, the same architecture can be used to do for compression, feature learning, clustering, regression, and classification. So it is different from a traditional method. Traditional method usually say different tasks should have different network architectures, different algorithm. So for ERM, actually the same network architecture used for all these cases. So in general, in the published paper also have these kind of figures. Traditional, we have the neural network method, feature space method, and biological learning. So they are all different. So there exist significant gaps among them. So in our published paper, we show actually neural networks, many neural network method, even the feature learning method, including the PCA, SVM, etc., actually can be simplified. We remove those redundant things, irrelevant, so-called unnecessary aspects. Actually, we can use ERM to replace them. And then in our paper, we already proved all this actually provides suboptimal solutions. And then 3 years ago, actually 2 years ago, in the Nature, one paper talked about the so-called biological learning. So they found that in the rats olfactory system, actually the neurons in rats olfactory system are random generated. So this is exactly as predicted in the ERM series. Because 10 years ago, we proved, say, as long as the neuron is a random generate, so-called occurring function, nonlinear piecewise continuous, no matter whether you know the exact formula or not, right, including biological learning. So the learning can be done without tuning the hidden layers, hidden neurons. So then that's 2 years ago, one paper published in Nature exactly verified, confirmed the ERM theory. Okay, so in general, ERMs filling the gaps among the different learning algorithms. So have the 3 aspects. The first, we'll talk about the hidden neurons. Hidden neurons are important, but hidden neurons can be, needn't be tuned. It can be so-called neuron just inherited from the ancestors through the DNA, gene, etc. The hidden layer can be random generated, or hidden layer can be kernels. The second, we talk about ERM architecture. It could be a single hidden layer feeder for neural level, generalized, right? Even the hidden node itself could be a sublevel, or it could be multi-layer. And then third, we talk about the structural risk minimization and ridge regression theory. And then last one, we wish to provide a homogeneous learning algorithm for compression, fiction learning, clustering, regression, and classification. So with this, we see the brain already very complicated, but layer by layer. Each layer actually overall is structured, but each layer could be the, is very messy, disorder. Although it is messy and disorder, according to the ERM theory, NAP can provide all those functions, right? So in general, we compare the biological learning and ERM. We will see there actually a lot of features, properties are convergent. For example, we just mentioned biological learning are very stable in wide range of neurons. Actually, ERM also very stable in a wide type of number of neurons. And the ERM actually very easy for parallel implementation and hardware implementation because the hidden neuron needed to be tuning, right? And then finally, your ERM actually is not very sensitive to the user-specified parameters. And then we always can come out the hardware first before we see the applications. So compare is the Newman. Newman actually have we also published paper this year, last year. But Newman also is father of computers. He has a father. So why the brain looks imperfect, but can have the learning capability, right? Much smarter than human. So according to the ERM theory, the ERM theory tells us overall the brain actually is structured, right? Either come from the inherited from ancestors, but locally could be disordered, random. Okay, so I just spent 2 minutes talk about the potential integration with the IoT and also the relationship between machine intelligence and human intelligence. So we say Internet of Things and animation. Actually, 3 portions, 3 parts. The first is data, right? Second is the sense, the things, okay? The second is the data analytics, okay? And the third, intellect. Of course, we are not care about the intellect now. Actually, 2 portions we can do from data analytics point of view, the things and data analytics. But since we can have the machine learning techniques embedded, so then become intelligent things, okay? So then the second, when we have intelligent things, actually like a human, things and things can talk to each other. These things, this algorithm embedded should be parameter, not so sensitive parameter, because the smart thing, the things, the environment so diversing. So things can be talk to each other. Then we have like a human, society of human. We have a society of intelligent things. So intelligence, Internet of Things, I think have the 3 steps. Now Internet of Things, then we should have the Internet of Intelligent Things. Then like similar to society of human, we should have the society of intelligent things in the future. So finally, I give some observation between the machine intelligence and human intelligence. You see, we know that machine intelligence become higher and higher. It beat human in more and more applications. I think it's not surprising. In the future, we will, will be beat by machine in many applications. But meanwhile, I thought actually human intelligence actually going down further and further. You see, before we have the smartphone, how many so-called phone numbers could we remember? We can easily remember 20 phone numbers. But now, how many of we can remember 5 phone numbers? Very difficult, right? Many times we look at our phone, etc. So that means, I just give up, that means all intelligence somehow, of course, this memory is one of the intelligence, actually become have been lower down, right? So, but machine intelligence become higher. So this is why I say I'm worried about when we talk about AI, when we talk about machine intelligence, actually we should worry about our own intelligence, okay? But in the end, I think when we talk about these two society, human society and machine society, what I call society of intelligence, actually overall intelligence of the combination of these two society will be improved. For example, although we can't remember 20 phone numbers, but can we remember 1,000 phone numbers? For example, your phone itself can remember 1,000 or 2,000 phone numbers. With the aid of the phone, smartphone, I mean the machine intelligence, or intelligence itself, right? Overall intelligence increase as well. Okay, so that's the end of my talk. Thank you.